So I'm very happy to introduce Rafael Potrie, who will give us now the second lecture of his mini course on collapsed Anosov flows.
Okay, thank you, Luna. And so I will continue with the mini course. So last time I gave some examples of partially hyperbolic systems, which had some algebraic nature. And so today I want to produce and explain some constructions of partially hyperbolic systems, which are not of algebraic nature. But in any case, so the construction of these objects will be made through deformations and constructions whose building blocks are algebraic systems or geometric systems in any case. So the first family of examples that comes to mind is the family of Anosov flows. And since I'm restricting in 3 dimensions, I will start by doing it from the very start. And so we'll consider a closed tree manifold. And if we have a flow on the manifold, we will say it's an Anosov flow if it verifies this property. Okay, so it's a property which is very similar to the partially hyperbolic property. It involves the differential of the flow preserving a splitting in the tangent bundle into one-dimensional subbundles, and which has some contraction and expansion properties. Notice that since the flow, it's a non-singular flow. Okay, so let me emphasize that, singular. And since it doesn't have singularities, we don't need to require anything on the behavior in the center direction, because it will be automatic. And so the family of Anosov flows contains, for example, the geodesic flow that we discussed last time, and that Gerard is working in negative curvature. But it also contains other families of examples, in particular algebraic examples, such as suspension of linear automorphisms of tora. But besides these algebraic constructions, there are many other Anosov flows in tree manifolds that are constructed by starting with these algebraic examples and making some tertiary constructions and cut and paste topology, producing a very big zoo of examples. And already the understanding of Anosov flows in tree manifolds, it's a quite open theory, which is pretty fascinating and very interesting. There are many interesting questions, but in this mini course, I won't enter into this. Okay, so Anosov flows will just be something given that we will feed into our machinery and to the things that we are understanding. So we will assume that the understanding of Anosov flows belongs to someone else. Okay, so and we don't care about this. So if we compare something to an Anosov flow, we will think of it as well understood. And so since it's a mini course, I wanted to give an exercise. So in case you get bored, and the exercise is doable, but not totally obvious. And the exercise consists on taking an Anosov flow and fixing a smooth function, which is positive, and considering the map of the manifold such that f of x is phi tau of x of x. Of course, and here is I'm asking you to show that this map is partially hyperbolic, but of course you need to find condition on tau so that f is a diffeomorphism. So in particular, this exercise is presupposing that you first did this exercise of finding a condition on the function tau, so that the map I'm defining here, which is you have a flow and you flow a different amount of time through every point, and for some smooth functions this will be a diffeomorphism. Okay, and my claim is that whenever this map is a diffeomorphism, then this diffeomorphism will be partially hyperbolic. Okay, so this is a doable exercise, but a non-trivial exercise. So, and what we will discuss in the rest of this lecture could be a way to approach proving this.
Sorry, Rafael.
So why is not constant?
If it's constant, then if it's constant, it's okay. But I'm saying, so first, the exercise has two parts. First, find a condition on tau so that F is a diffeomorphism. And the second one is show that if tau satisfies this condition, then F is partially hyperbolic. Okay, if it's constant, it's a much easier exercise.
So your second exercise, you're assuming still a smoothness, yes? So you're saying, is it?
Yeah.
Can we?
Is probably one condition that you need to ask. So I'm putting this condition in purpose so that you don't need to be careful about the other things. Okay,
is it reasonable to ask the following question? If you have some continuous function and you know that F is diffeomorphism, then if it is not constant, is it partial hyperbolic or not? Do we know anything?
If it doesn't, if it's positive, continuous, and F is a diffeomorphism, then it's also partially hyperbolic. Exactly. The same proof will work. Yeah, but I don't want to enter into that. So this is a family of examples. It's not the most general family of examples, and in particular, one of the reasons one does not. So I wrote here a keyword saying discretize Anosov flows, which is not exactly this. So the right definition of discretize Anosov flows is not this one. And the reason is that this class of examples is not an open class in the space of partially hyperbolic diffeomorphisms. And so you need to create different categories of objects, but I don't want to enter into that so much. I just want to put this exercise because what I will do in the rest of the talk also is a way to address this kind of problems. Okay, and so that you can have this problem in mind, which I want resolve. Okay, but this is a family of examples, and it's more general in principle than just taking the time one map of an Anosov flow. Okay. Okay, and as I said, so the main way that we will use to construct new example will be to make deformation of known examples. And we will use crucially the fact that partially hyperbolic diffeomorphisms are open, and more importantly, the reason why partially hyperbolic diffeomorphisms are open. So now I will discuss exactly this reason, why partially hyperbolic diffeomorphisms form an open set of the space of diffeomorphisms. And this is called the cone-field theory. Okay, so we take a Riemannian manifold, we take a continuous subbundle inside the Riemannian manifold and a continuous function from 0 to 1. This is like an angle. And so we will define a cone field, which depends on this bundle and this angle, to be for each x in the manifold, we will associate the set of vectors which make angle larger than alpha. Not angle, so this is the cosine of the angle, I don't know. So which are close enough to the bundle E, okay? And I will add 0 just to add this vector, because 0 doesn't make sense here because I'm dividing by the norm. And so the and the interior of the cone field will be taking the strict inequality here and also adding 0. That's because if I don't add 0, then it's not invariant. This is just one way of the many ways you have to do this. Okay, so is it clear what a cone field is? This is not the most general way to define a cone field, but we'll take at each point a subbundle, and then we'll take the set of vectors which may make a small angle with respect to this subbundle. And the cone field criteria says that a diffeomorphism is partially hyperbolic if and only if, and here I'm restricting to dimension 3, you have 2 one-dimensional bundles which are quasi-transverse, so they don't intersect, and there are cone fields around these subbundles which have the following properties. On the one hand, so the C1 cone field will be what we call the unstable cone field, and it's invariant under df to some iterate. So the cone is mapped into its interior, and vectors inside the cone are expanded. And similarly, C2, which is the stable cone field, will be invariant under the pre-image of df.
Rafael,
yes.
Probably, sorry, a silly question. Why are you are not considering the constant function? Why are you not interested in have continuous function?
Yes, so that's a very good question. So the same statement, the same statement works if I consider the constant function, because also I'm taking this n here, which allows it. So there are many equivalent ways to present this criteria, and I think I had a reason to do it this way when I did, but I don't remember it now. But
good. Okay.
But I thought about this, and I think I had one reason, and maybe we will see it later. But it's equivalent, and that's another.
Okay. I asked you why. So okay.
Yeah. And
sorry,
I think, yes.
Sorry, is this equivalence with pointwise partial hyperbolicity or absolute?
Okay, also good question. So this is pointwise partial hyperbolicity,
okay.
and which is so I won't enter into being very precise about these distinctions. There are subtle differences between definitions. I think the natural one is this one for many reasons, in particular because this is the kind of condition that is implied by robust properties, such as robust transitivity and stuff like that. But so, okay, it's my fault. I'm being very technical, and so this makes this quite technical. But I just want to keep the drawing, okay? And the drawing is that what you have to have in mind is that you have a family of cones that depends on the point, and when you apply the derivative, this C1 cone is mapped inside the C1 cone in the forward orbit, and the vectors here are all expanded, say, by 2. And similarly for the backward iterates. And of course, this is a very coarse condition. So if a map has the derivative very close to the derivative we have in these coordinates, then it will still have this property. So this is it's very easy to see that this gives you how do you say, an open condition in the space of diffeomorphisms. Okay, so maybe, okay, this is the actual statement. There are many variations of this statement which are possible and equivalent, but the thing to have in mind, and all the thing I will use in the proofs, is this drawing, okay? That you need these two bundles, and to the remark that the stable direction will be contained in this cone field, but it also will be contained in the pre-images of this cone field. C2 for every n, okay? Because I will explain how the proof goes, and so these cones you can start to iterate and make them smaller and smaller to approximate better and better these bundles. Okay, so for every epsilon you will find a good approximation using these cones of the bundles. And here, what I'm also saying, so the center stable direction will be contained in the pre-images of the complement of this bundle, and the center and so I'm here finding ES and EU, but indirectly I'm also finding the center direction. Okay, if I wanted a version of this cone field criteria that gives you this absolute partial hyperbolicity, for instance, I would need to ask conditions like this inside the bundles and inside the vectors inside and outside the cone field, and try to make comparisons of this kind. Okay, so and the criteria becomes more delicate, but you have equivalent criteria for this kind of things. Okay, as I said, this criteria has the consequence that the space of partially hyperbolic diffeomorphisms on a manifold is an open subset. And in particular, small perturbation of algebraic examples that we discussed last time will be partially hyperbolic. So let me explain the idea of the proof. And the idea of the proof is that you stand on a point X, and you will define the unstable direction as you go to f minus n of x, and then you iterate by df to the n. And as you do this, the cone will start to shrink until you get the unstable direction. Okay, in order to show that this shrinks to that the angle goes to 0, you need to make some linear algebra consideration. It's like when you do Schwarz lemma in complex things and stuff like that. So if you have a map that maps a disk inside its interior, then it's a contraction for some suitable metric in the projective space. And this way you can show that you cannot have the cone field getting thinner and converging to a fixed cone in the limit. Okay, and this way that is not a trivial argument. So but it's something that you can show. There in the notes I left for the mini course, you can find proofs of this criteria. But the important thing is that the unstable direction will be determined by this intersection, and the center stable direction will be determined by going to the future and iterating the complement of this cone to the point X, and you will approximate the center stable direction. And since this is a nested intersection of subsets, this will give you very good approximation of the bundles, as good as you want. This is what I wrote here, that this cone field approaches the unstable direction, and the same with the rest. And so the general principle that maybe we should try to use here is, now once you have these cone fields, and then it's not really the fact that you are C1 or C0 close to your map that makes you keep the partial hyperbolicity. It's only the fact that you preserve the same cone field. And this is what I informally like to say, that you can do perturbations which are C1 small but C0 very big. Okay, and this is a general principle, and one very easy to prove proposition, but it's an important remark in our work, with which we did with Bonatti, Gogolev, and Hammerlingel, is that if you have a partially hyperbolic diffeomorphism and you have a diffeomorphism of the manifold, which sends the unstable direction of F transversally to the center stable direction and the stable direction of F to transverse to the center unstable direction, then by composing with phi, which may be a very large map, the composition is still partially hyperbolic. Okay, so the first example you can think of verifying this kind of criteria for whoever knows this example is Magnier's example. So if you take and derive from Anosov example, so this remark is already present in those examples from the TA that I think it goes back even to Smail and Magnier and Schub, and there are many examples on which the key remark is that if you do a C0 a C0 small perturbation, then you control the image of the points. And so if you preserve the cone fields by the derivative, then you will keep, the map will still be partially hyperbolic. So here we are, instead of using C0 deformation, so the key point is, if you are able to understand very well the bundles of your partially hyperbolic system, then you can decide which diffeomorphisms will preserve the fact that you are partially hyperbolic. Okay. And so let me explain the proof of this. So is this, I think, so this is the statement I want to show. If you have a partially hyperbolic diffeomorphism, and a map phi, which respects the transversality of the bundles, then for a large iterate, you will have that phi composed with f to the n is also partially hyperbolic. Okay, and it's very convenient to work with this. So to divide this n in two pieces and apply it here and here. Okay, which is conjugate, because if you conjugate this map by f, you put here f to the n and here f to the minus n, you get this one. So they are smoothly conjugate. So it's the same to show that this one is partially hyperbolic, that this one is partially hyperbolic. Okay, and so the way to make the proof is you will take the cone fields that are ensured for your partially hyperbolic diffeomorphism f, and if you take n sufficiently large, these cone fields will be very close to the unstable direction. So for instance, df to the n of C1 will be very close to the unstable direction. So when you apply phi, so you apply this one, and the cone field will be very close to the unstable direction. So close that when you apply phi, which has this transversality property, will map the cone field transversally to this guy. And then, since it's transferred to this, then if you apply f sufficiently many times, then you will be again inside the cone. So let me make this as a drawing. So you start with the cone field C1, you apply the df to the n sufficiently many times, and then you have a very narrow cone field here, which you know that phi will make it transverse to the center unstable direction. But then if you are transverse to the center unstable direction, if you apply df to the n many times, eventually you will be inside the initial cone field. So if you do this both for C1 and for C2, then you will automatically get the cone field criteria, and so this map will be partially hyperbolic. Okay, so one thing that needs to be, so it's not that I'm not showing that phi composed with f is partially hyperbolic. And this is something that may be bad. But since we will take f to be an Anosov flow, at least we will be able to control, no matter which n we take, the isotopy class of this guy is very well controlled, because it's a flow, so it's isotopic to identity. So if we find a map phi with these properties, which is not isotopic to the identity, we are really creating some new stuff. Okay, that's the key point. Okay, so before I explain how to use this criteria, let me tell you about some natural object that we kind of, at least I was not very aware of, and I think it's very interesting to understand, and it has, and somewhat the point of this mini course is to explain that it has a very strong link to partially hyperbolic diffeomorphism. So a self-orbit equivalence of an Anosov flow is just a permutation. It's a homeomorphism of the manifold which permutes the orbits of the flow. Okay, so the identity, for instance, is a self-orbit equivalence, and flowing the map that we define today is if you have tau a function like this, smooth, continuous here only, then beta of x defined as phi tau of x, this is a self-orbit equivalence, if it's a homeomorphism. But there are more interesting examples which actually permute the orbit. So take one orbit into a different orbit. Okay, so let me give you the first trivial example, the relationship of this example with partially hyperbolic dynamics was explained in a paper by Bonatti and Wilkins. And so you take an Anosov flow, for instance, the geodesic flow that we constructed yesterday, and you take a finite cover of your manifold to a finite leaf. So flows are vector fields. So vector field you can lift to a finite cover, and it will give you a new flow, which as you are lifting the metric, it's still an Anosov flow. You lift all the bundles, and the conditions are still verified. But now, any deck transformation of this finite cover will be a self-orbit equivalence of phi t, because it will map orbits of the flow into a different orbit of the flow. And in fact, if you take one of these deck transformation and you compose with some time of the flow, you will always get a partially hyperbolic diffeomorphism, which is not the time one map or similar to the time discretized Anosov flow in the sense I discussed at the beginning. But also let me point out that self-orbit equivalents like this, in particular that they are smooth, are very rare. Typically, one can show that if you have an Anosov flow and you have a self-orbit equivalence, which is a diffeomorphism instead of a homeomorphism, which was what we actually asked for in the definition, then it's an iterate so that it's the trivial self-orbit equivalence. And this tells you, so okay, if this is not so different from the trivial orbit equivalent, because if you have a map like this, then you iterate and eventually you are the time one map of an Anosov flow. But there are other examples way more interesting of self-orbit equivalence, which are not periodic. And the question is whether you can produce partially hyperbolic systems using these self-orbit equivalences. Okay, so for the time being, we know some non-periodic self-orbit equivalence, and there's a recent paper. I'm not sure self-orbit equivalences were studied as an object before a recent paper by Bartelme and Gogolev, where they started the study of these maps, and they classified the ones which are homotopic to identity. So recently there's also some work by Bartelme and Katie Mann on this, and now it's a very natural question that it's being explored. So let me tell you that, so the criteria we gave will allow us, so in tomorrow's lecture, to produce new self-orbit equivalences that were not considered before by creating partially hyperbolic systems, which were also not known. Okay, so let me, in the rest of the talk, try to explain how to produce these new examples, and I will restrict to the case of the unit tangent bundle of the surface that I discussed last time. Okay, so the notion, so in order to make a proof of what I want to show.
Rafael, I'm sorry, can I interrupt you?
Yes,
About
yes.
this, you said that if the self-orbit equivalence is smooth or differentiable, no, diffeomorphism maybe, yes.
It's a diffeomorphism.
Diffeomorphism, then it should be really periodic. Do you assume something on your manifold, or you're taking a finite cover?
Three manifold, yeah. It's a three manifold, and you have an Anosov flow there, and you take as if you have a self-orbit equivalence, which is a diffeomorphism, then it's periodic. Essentially, it means that it's like this example.
That you permute.
You are permuting the
transformation.
Yeah.
Nice. This is Barthelme family. What is the paper? BFP Barthelme family.
So this is the paper the mini course is about. It's called Collapse Anosov Flows and Self-Orbit.
Okay, the paper. Okay.
Yeah, I will mention this paper later. So okay.
Thank you.
And so the notion I want to introduce, which is a notion that we introduced in this paper with Christian, Andre, and Andy, it's called the phi transversality. In fact, so in this paper we called it H transversality, but now I will use H for a different thing, so I'm changing the name. And the notion is the following. It's essentially the same notion that appears in this remark, which is you have these transversalities, but now I will allow the partially hyperbolic systems to be different, not even in the same manifold. Okay, so you have one partially hyperbolic diffeomorphism here, another partially hyperbolic diffeomorphism in a different manifold. The manifolds are diffeomorphic, so they are the same manifold essentially, but I don't want to remember that they are the same manifold, because, for instance, in the case of T1s, what I will do is I will change the Riemannian metric, and so I will think of them as a different manifold. And at diffeomorphism, we will use this notation to say that this maps the unstable direction of F transverse to the center stable direction of G, and the inverse maps the stable direction of G transverse to the center unstable of F. And the reason this is convenient is that we are going to show that you can compose these things. And so this way, you can go from one diffeomorphism to itself by doing a lot of things. And in the middle, eventually you will do something non-trivial. And so the restatement of the proposition we just showed is that if you have F is phi transverse to itself, then there's an n such that for large enough n, this map is partially hyperbolic. So with this notion, what we just proved is exactly this. And so the key proposition in our paper is that if you have three partially hyperbolic diffeomorphisms and you have these conditions, then you can put something between F and H. So there's like a transitive relation between these things. Okay. So let me say it again. So you have three partially hyperbolic diffeomorphisms. You have a diffeomorphism that makes the bundles of F So you can think of this for a mnemotechnic way to understand it is phi maps the bundles of E of F very close to the ones of she. Okay, if phi preserves maps the center stable to the center stable, the unstable to unstable, then that's perfect. So, but if it's more or less like that, then it's okay. And then the reason you can compose is exactly the same game as we did here, because you will have the unstable will be mapped transverse to the center stable, and then if you apply she long enough, then the bundle will approach the unstable again, and then it will become transverse to the other one. Okay, so this is really an exercise. It's the same proof as we did, but it's a very important remark, because it will allow us to show the following theorem, which I think now is really I think a non-trivial theorem. Tells you that if you have a closed surface, there are more general versions, but this statement is, if you have a closed surface of genus G, you have a diffeomorphism of the surface, no matter which diffeomorphism you choose, then there exists a partially hyperbolic diffeomorphism in this manifold, which is isotopic to the lift of the map rho. And the one reason this is non-trivial is that before the only examples we knew here of partially hyperbolic systems, and the ones we believe that exist, were all isotopic to the identity. And so now we are producing, for every mapping class element in the surface, we are producing new examples of partially hyperbolic diffeomorphisms. Okay, and next time we will see how this construction relates with the geodesic flow and its self-orbit equivalences, because that was something that we had to do once we had the new examples. So how can we explain these examples? How can we describe them? Okay, so I have 7 minutes. I will explain the proof of this theorem. So, and this proof is not the one we wrote in our paper. So we added a remark when we received the report, because it's a simplification that was suggested to us by Livio Flaminio, which is actually much simpler than what we did. So what the reason we did a different way, because we already had some mapping classes that we could do, and then we started to try to compose these mapping classes. And so it was natural for us when we understood this concept to do it that way. But with this concept in hand, we should have forgotten about what we knew before. And the right proof is the one I will give now. And so if you take a hyperbolic metric on the surface and its geodesic flow. So this is an Anosov flow. In particular, if you take as t, say t = 1, this is a partially hyperbolic diffeomorphism. And we have this diffeomorphism of the surface, rho. So this induces a new metric on the surface, given by the pullback of the metric mu by rho. And we denote by phi mu hat t the geodesic flow of this metric. The metric is still the two surfaces that we have, they are isometric. So phi rho is an isometry between them. So it's still constant negative curvature. They are different realizations of the same point of the Teichmüller space, if you want. So they are both surfaces with constant negative curvature, but they are not the same. So there's a diffeomorphism changing the points from one to the other. And with the node by phi mu hat t, it's geodesic flow, which is also partially hyperbolic. But then you can compute essentially the isometry is an isometry, and so it preserves all the properties of the geodesic flow from one to the other. And so it's actually much better than this property. We are actually sending the centers, the stable, the center, and the unstable direction of this flow by this map to the center, stable, and unstable of this map here. Okay, so here I'm hiding something that has to be taken into account. That so formally, and this is what I said before, you don't need to think that the manifold is exactly the same, because essentially the unit tangent bundle of the surface formally depends on the metric, because it's the set of vectors of norm 1. Okay.
Preserve, sorry, the parameterization also?
What?
The parameterization.
Yes, this is a smooth conjugacy between the Anosov flows. Okay? But it's like when you are doing, so there is this Teichmüller space, which is a ball, and then you have the metrics up to, so there's the modular space and the Teichmüller space. And so here you are actually changing the way you are fitting the metric in the surface, but it's the same metric up to diffeomorphism, only that the diffeomorphism is not isotopic to identity. And so and it's really a conjugacy, a smooth conjugacy between these two Anosov flows, and therefore you preserve all the bundles, and so you have this property. And then, of course, we use the fact that the space of metrics of negative curvature is connected to find a path that goes from the original metric, from the final metric to the original one. And so you can find a path of metrics that goes from one to the other. And with the node as phi s of t to the geodesic flow of the metric mu s. So you have this path of metrics, and you have a path of geodesic flows. The point is these geodesic flows are now moving continuously, and so the bundles move continuously. Since the bundles move continuously, if you make a coarse enough partition of the interval, then the bundles will be very close. And so the identity will work as a transversality between one and the other. Okay, because it's you have the flow here. This is phi sk, so si of t, and then if you move the metric very little, then the bundles move continuously with respect to this parameter, and so the identity will keep the fact that the unstable of one is transverse to the other. And so now we can compose this. So we found this. We had this phi, say phi 1 of mu is transverse to phi 1 of mu hat, and then we started doing a lot of another partially hyperbolic guys and putting the identity here, and eventually we came back to phi mu of 1. And if we apply the previous proposition, we can compose all of these guys. And to compose all of these guys, we get a map which has the following form: is first we apply the rho, and then to compose the things, we had to apply the middle guy sometime to correct the bundles. So to go together with the correction is moving with itself. And so we will find very long times, say T0, T1, Tk, so that this guy makes a transversality of the geodesic flow with itself. And as we showed, this gives that for large T, we have that phi composite phi mu T plus phi mu T is partially hyperbolic. And this is isotopic to D rho. Okay, so time is finished, so I will stop here. Thank you.
Wait. So you use the geodesic flow to do the funny. Sorry, so you're using the geodesic flows with T really large in a way to be correcting.
Yes, yeah, these are all different geodesic flows. I'm
Yes.
changing the metric and I'm applying the geodesic flow a long time so that I correct the bundles and then apply again the other one and I correct the bundles with the other, I correct, and eventually I come back and
They are all geodesic flow that they are conjugate one to the other, no? In certain
they
way.
are smoothly conjugate, but they are not the same. And so I'm
clear.
applying different partially hyperbolic systems and by this cone criteria, at the very end, I know that the guy is partially hyperbolic. But this is an important point. Right now, we kind of know nothing about this example other than it's partially hyperbolic.
So it's like if you do the same idea of for Anosov diffeomorphisms, you are taking correction of Anosov diffeomorphism and started with any diffeomorphism d phi that you want.
Yes, and that is a problem because if I do Anosov diffeomorphism, since I need to correct with the guy, then the isotopy class I lose control.
Yes, good. But here you remain in the control because you know that at the end everybody is isotopic to the identity, so they finish being isotopic to the phi.
Yes.
Good.
Let's thank the speaker.
I have a question.
Yes. But I wanted to thank him for then opening the question. In other case, he's going to miss a clap of hands. So now we open for question again. Lorenzo?
First, I apologize by my question, Rafael, because this proof that you gave is wonderful, extremely elegant. But I am afraid that when you have a very elegant proof, you miss something. It's possible to say some words about the original proof that probably is much less elegant, but maybe you can say something more behind the proof. Again, I apologize by this.
No. I understand your point, and I think one of the points is that up to here, we know very little about the argument, and the other proof it's less elegant and it doesn't clarify anything. So the point is that before we knew by hand, we had an argument to show that certain den twists on certain hyperbolic metrics, we could do the transversality, and that was by hand because we understood where the bundles were, and so we could find some map by hand. It was like a brute force argument that allows to show that you have the transversality, and so you have that. And then we use that any mapping class is made by composition of den twists on different metrics, and we had to play around. So all the arguments here were contained in our proof, but it was more complicated because we had to put a den twist at each point and then change the metric so that we had a very small angle and then make the den twist. So in fact, we could see even less what was happening. And I guess, so the point of the next two lectures is try to give some insight on how can we understand these examples.
This proof should work in any, you don't need to start with a surface. You can start with a manifold that they have a diffeomorphy, that they have a negative curvature.
There is an issue, which is, so this I'm not sure, because in higher dimensions you can do more things, but for instance, if you have a hyperbolic tree manifold, and so the most of rigidity tells you that you don't have new isotopy classes. So this is very surface
I think in hyperbolic, in higher dimension, your result shows that you should be kind of isotopic to identity after some iteration.
Well, so no. In our results are only in dimension 3. If you go to higher dimension and you do the geodesic flow there, you get a 5-dimensional thing, and I don't know anything about that. I expect that maybe the self-orbit equivalence of higher dimensional Anosov flows are more rigid than in 3 dimensions, in the same way that Anosov flows are more rigid in higher dimensions than in dimension 3.
Yeah.
Not sure. There are this example of partially hyperbolic that is kind of the formation of the derived of Anosov. And so you have this partially hyperbolic geodesic flow, which are not hyperbolic geodesic flow. And you can start with this and start with this construction. So this means you can start in this construction that you're doing, you don't need to start with the hyperbolic geodesic flow. You can start with a truly partially hyperbolic geodesic flow.
Yes, I think this proposition is totally general, and it's very flexible. So it's a remark only. It's like a restatement of the Confield criteria. But I think it's very flexible, and many things can be done with this. I don't know.
Because the only observation was saying that you are starting with something that it's a, how do you say, geodesic flow that you know that is hyperbolic.
Yes.
But they're saying that you could be doing this trick, not necessarily with a hyperbolic geodesic flow, but with a truly partially hyperbolic geodesic flow.
Yes.
And we know that there exists truly partially hyperbolic geodesic flows. And then if you have this criterion or transversality criterion, maybe you produce something that is not in the class of hyperbolic geodesic flow.
Yes, it could be.
Is this example by or whatever?
Yes, I understand, but I think it's flexible, but I don't know.
Well, your student, Luis, is working on with this type of geodesic flows.
Yes.
And maybe he can build new type of partially hyperbolic with this construction.
Yes.
Lorenzo had more questions.
Or it was me, but
Potrie, sorry.
It's much more simple. Earlier you mentioned that this proof of the existence of line fields, invariant line fields in the cone fields uses some, you go to the projective space and have some arguments, and you refer to some course nodes. Which nodes are those? Also these collapsed Anosov flows, or?
No, so we wrote these lecture notes with Sylvain for a mini course, and there we wrote, but I think, so there are many proofs of this Confield criteria, and there are different ways to show it. The version I stated is a little bit more difficult to show than other versions, and you need to use some contraction in the Hilbert method, for instance.
Okay. Thank you.
I have a question. If you start with another metric close enough to the original metric, then you will have two partially hyperbolic diffeomorphisms. They are conjugated or not?
No, conjugate, no, but we will discuss some notion of equivalence. So in general, if you take, say, the Anosov times the identity on the circle, or even a time one map of a geodesic flow, you perturb even among flows, and you are not conjugate. You are orbit equivalent, okay? And so in partially hyperbolic dynamics, you need to take into account the center direction to discuss about equivalence. And you cannot expect that the center dynamics will be the same. And here, if I take different T, not even different metrics. If I take different t's here, I will get a different guide, which may be totally different from the original one. But the question is, so I will try to introduce what I think is the right question in order to say that these examples are all the same.
Okay, thank you.
More questions or remarks? Then let's thank Rafael again